We're going to move forwards with this lecture on reflection, where light begins to take a mathematical role in a field of physics called geometric optics. Geometric optics concerns itself with trying to trace back where light came from and forming these false images where there's no actual objects, just a perception of an object because all the light rays sort of came from one spot. This lecture is split into two parts. First, we're just going to talk about what a reflection is and how it's created, what it has to do with matter. And second, we'll get into the math of how to actually compute where and how big a reflection, an image from a reflection is. And this is very useful if you want to create or think about an optical device like well, of course, a mirror, but like even a microscope or a telescope, they have mirrors in them. They also have lenses. The math that we use for lenses is uh, identical, really, to a mirror's geometric optics analysis. So light, which we've talked about as being a wave of the electromagnetic field, can interact with matter in a few different ways. Whenever light hits something, three things really can happen: absorption, reflection, and refraction. Absorption, probably the most complicated, is where light hits matter and deposits its energy. The light no longer exists once it hits the matter, and that energy that was in the light now becomes something else since energy is conserved. This could be heat, usually, or some other, it could even be electricity in a photovoltaic, but the energy turns into some other form of energy and it's gone. And depending on the material, it'll like to absorb different kinds of light. Light can also reflect, and this is where light bounces off the surface, and we'll talk about exactly what that really means to reflect. And finally, light can refract, where it goes through. It's what's called transmitted. Light goes through, but it can be altered on the way through. Really, its pathway can bend, and that's for the next set of notes. The next two lectures really are about geometric optics, which is where we track where light was and where it came from, within a very sort of geometric and shapes and lines and triangles sort of way. Uh, but specifically about reflection, I wonder if you have thought, what really is a reflection? How does it work? Why are some things able to show you a clean picture of what you see, like a mirror, and other things don't really reflect that way, but they kind of, you can tell that light bounces off of those things. So what's happening at the surface of a reflective object? Well, to answer that question, we have to go back to what light really is. And so recall that it is a wave of the electric and magnetic field. So if we have these electric field, which is perpendicular to the direction of travel, then we'll also have a magnetic field. Altogether, though, this object is an electromagnetic wave or some sort of a piece of light that travels rightward. So maybe the red is B, the magnetic field, and blue is E, the electric field. And they're both going to travel in their rightward directions together. So a lot of the times it's really just as a point source of a bunch of light. So imagine like the sun or a light bulb, it's going to emit light in all directions, and that's what we're using these concentric circles to represent. Each circle is like a peak in the electric field, like this. Each of these is a peak in the electric field, and these arrows are rays, light rays, where the light is traveling outwards towards the center. And you can play with this wave idea with simulations here on PhET uh, to see. We'll play with it definitely later in two notes down the road, and we're more interested in the wave nature then. But yeah, we can represent light as being rays or arrows of light, essentially. In order to see something, we have to take in those rays into our optical devices, which we call eyes. And we need multiple rays together to form an image. You can see there's like two light rays here. Of course, there's an infinite number, or well, many light rays that enter your eyes that are coming from an object. Uh, and we will need multiple, and if it's far enough away, we'll see that these light rays are almost parallel, but not quite. And so we're going to be interested in this kind of a shape here, where there's multiple light rays that are nearly parallel going towards an optical device. Let's detour back to AC circuits for a second. We had this slide, just last notes, where we were driving an AC voltage across a piece of metal or like an antenna, which is going to actually send a signal. So we have that these separates the positive and negative charge if we're driving this piece of metal back and forth with a voltage, and that will create this electromagnetic field which will propagate outwards away from the antenna. Okay, and so think about what happens when it reaches another antenna over here, which is going to receive the signal, right? It's going to feel this electric field, which is then going to move the charges in the direction of the incoming field, which is obviously going to change over time. And so as it does this, we're going to detect a signal over on this antenna. But consider that antenna now, well, it has moving charge, doesn't it? Now that it's been attacked by this signal, these charges are going to move back and forth. That means that it also is going to be emitting its own electric and magnetic field and its own signal. It's going to repeat the signal since the electrons in there are moving. It sort of behaves like its own signal generator. In reality, though, this second wave is weak when we're far away from the antenna. The incoming electric field is much weaker than the original one that came away from the antenna. So you have to, when you build a signal, it has to be very, very powerful because it weakens as it gets further away from the source. It's going to be received at a low intensity. Well, this same thing happens not just in an antenna where we have the signal repeating, but it happens really in any piece of metal. If you think about it, a metal, the whole thing that made it a metal is that the electrons are really free, and that allows the easy flow of charge, right? Easy flow of current. When a signal, an electric field comes in and hits this piece of metal, the electrons will respond in kind, and they'll respond very easily. They'll wiggle back and forth in the same way that this incoming light was wiggling. And in doing so, it's going to repeat the signal and spread it out in all directions. Well, theoretically in all directions, but it's going to go out, and this is a reflection, right? So what it's this repeated electromagnetic wave when a material repeats the motion of the electron in an original signal. Metals are really reflective, right? Because exactly this, they like the electrons there are very free and they are able to move and react to the incoming signal. Non-metal objects are a little bit less free, and so they can partially reflect or partially let light through, but metals are really good at allowing their electrons to move free. This reflection can be split into two kinds depending on the surface of the reflecting medium. So this is probably what you are more used to thinking of as a reflection. A specular reflection is one that preserves an image and it forms a nice crisp reflection of this, this building right here. However, a diffuse reflection doesn't really doesn't really give us a nice crisp image. Here we see that the sunflower, it's yellow and it's green. Well, it needed some light to shine on it in order to be seen. So it's reflecting light from the sun. The yellow light you see came from the sun, but then was reflected by the sunflower petals. It's not going to preserve an image that you can recognize of the light that's incoming. And so for specular light, what happens is the surface is nice and flat, and so light that comes in comes out at the same direction uh, all together. Whereas in a diffuse reflection, because the surface is so rough, usually this is the reason here, light comes in and it's going to bounce off in all sorts of random directions, and so that outgoing light doesn't preserve the image of the object that it's giving it the light. So for specular reflections, think of metallic things, think of water, very flat, shiny surfaces like ceramic. But for diffuse, think of just something dull like drywall, your skin, and most things that you see actually are not specularly, diffusely reflecting. They also do a little bit of a specular reflection. You might be able to see, if you look at a wall, you might be able to see some semblance of the light source striking the wall uh, on top of just this dull coloring to it. About the math, it turns out that light reflects in a very simple way, called the law of reflection, and that says that light coming in towards a surface reflects exactly outwards at the same exact angle. Theta I is the incident angle, and theta R is the reflected angle, and we measure these with respect to a normal, a line which is perpendicular to the surface off which we are reflecting. And so it's a very simple law and a simple idea that we're going to move forwards and create some more interesting things with. For specular reflection, we have what's called an image. And so this is the ghostly thing created inside of this mirror dimension that an object sort of creates as the light from the object bounces off the mirror. Your brain is really smart. I promise, I know it is. And it's really good at distinguishing that this is actually fake and this one is real. But I want you to try to turn your brain off. Turn it on in a few seconds, okay? But turn it off and imagine that this is a perfect little mirror. Your brain would have no way of distinguishing the two objects. They are doing the same thing. They sort of look the same. And so your brain actually does a lot of processing power to be able to distinguish a fake object, which we call an image, in this sort of mirror dimension. Our brain uses context clues to be able to tell what's fake and what's real. Light carries no information. If I had a mechanical device that had no sort of brain to it, it would be impossible to tell if this was a perfect mirror. It would be impossible to tell which apple is real and which apple is fake without giving it some sort of context logic. I'm going to be talking about that mirror dimension a lot, or this mirror world. It kind of helps understand how geometric optics works. But yeah, we'll see that we're going to follow the simple law of reflection, and we can use that to trace where an object is based on its image or some other complicated convolution of these ideas. So if we have this shape, right, the shape here is helpful because it separates, right, the green light from the red. Both this green and this red and everywhere in between of this object is going to emit light in all sorts of direction, right? But one specific light ray is going to hit the mirror in such a way that it bounces off due to the law of reflection exactly into our eyeball and we are able to perceive it. A different part of the object is going to do the same thing, but it's a different angle that we need to be able to perceive it. So as our eye scans the mirror, our eye goes from bottom to top here, it sees the red and the green in this place as if it was in this location way over here. And so this is the image that we see. Light isn't really coming from here. This is behind the mirror, so it's not really coming from there. Light's coming from the left object and then being reflected in such a way that it looks like it was coming from the right-hand side. The object is the real tangible thing on the left-hand side here. And for a little bit more on the language here, DO is what's called the object distance. That's the distance in meters or something away from the mirror. Right here is the object distance. The image is a false object here. It's not really here, and it's created on the right-hand side in this case, and we have an image distance, and those two are going to be related in some way. DO is going to be related to DI. Oftentimes, that's going to be one of the main things we want to find is how far away is this image going to be created, or vice versa. Can we use the reflection to be able to compute where exactly an object is? For flat mirrors or plane mirrors, there are a few things we can note about the image that's created. So the image is going to be upright, but reversed right to left. You can see your own reflection if if you hold up your right hand, it looks like it's holding up its left hand. It's the same size as the object, so this height, the reflection's height, is equal to the original object's height, even though since it's farther away, it might look smaller. And it's just as far as the object is to the mirror, so DO equals DI. And the images are virtual. What that means is if you think about this mirror, right, there's no way that light is actually being reflected on the right-hand side of the mirror. That doesn't make sense. And so if you put your hand or a screen or something right here, put something right here, a real object, light is not going to be able to hit that object from the reflection. And so there's no actual light right there. This isn't always going to be the case, as we'll see pretty soon here. But before that, we'll look at a little example with a flat mirror involving some reflections, and we'll ask questions about distances. So a child is 5 meters away from their 10-centimeter tall toy truck. They are 12 meters away from a flat mirror. The truck is between the child and the mirror. So this is definitely a problem that we're going to want to draw in order to try and understand. We'll have to be careful. Sometimes this is the kind of problem where I can give you superfluous information or red herrings that you won't actually use. So here is the child. Here is the toy truck. And they are, let's see, 5 meters away. So this is a 5-meter distance. And this toy truck is 10 centimeters tall. Let's give it some wheels. And they are 12 meters away from a flat mirror. So here is a flat mirror. Let's actually move all this so that we give ourselves some space here. This is supposed to be 12 meters. And the reason that we're moving it is because, well, there's going to be a mirror dimension with a toy truck. Let's go ahead and label these again. CT. A toy truck over here. Oh boy, I didn't think about this when I drew the truck. I'll have to draw it again. And of course, the image of the child as well. Over here. Okay, so now we have our reflections and our mirror dimension child. I'll call him CI and TI for truck image and child image. So how tall is the truck's reflection? Well, in a flat mirror, reflections are just as tall as their original counterparts. They just might look smaller because they're further away. So the truck should also be 10 centimeters tall, just like the original object. How far is the child from their own reflection? Well, in flat mirrors, distances away from the mirror, an object's distance away from the mirror is going to be equal to the image's distance away from the mirror. So this should also be 12 meters as well. And so these first two, we were able to knock away really quickly with these rules on flat mirrors. How far is the child from the truck's reflection? This one is just a touch more tricky. Well, since the truck is 5 meters away from the child, and the child is 12 meters away from the mirror, we can use this over here. Let me draw in red. Over here, this distance from the truck to the mirror is 12 minus 5, or 7 meters. That's the only way to make this work geometrically. And you see now why you have to draw the image, well, this whole picture, or else these kinds of questions aren't as easy. And then, since that's 7 meters, that means that this is 7 meters as well, the image from the mirror to the truck. And the question is, how far is the child from the truck's reflection? That's this guy. So 12 meters plus this 7 meters means that the distance together is 19 meters to the truck's reflection. Hopefully that one makes sense. Flat mirrors are nice and easy mathematically, which is why it's much more interesting when you curve a mirror like what you might get at a funhouse mirror like this, where you can have small and large pictures of yourself. And so flat mirrors are nice mathematically, but spherical or curved mirrors are much more useful when you're trying to manipulate the light and not just pass a reflection on. So a spherical mirror is a common way to cut a mirror and have it be curved. Now I'm going to give you one little warning. I have an issue. Uh, I don't know what it is, but sometimes I call my elbow my shoulder and my shoulder my elbow. Something is hardwired. There's some sort of a crossing in my brain that doesn't really work quite well. Sometimes I do the same thing with mirrors and lenses. If you hear me say lens in this lecture, well, hopefully I haven't. Hopefully I found them and removed it. But what I really mean is mirror. Mirror and lens, I tend to flip them around. We'll see in the next set of notes that that's because the math is so simple, or it's so easy in how to transfer from one to the other. They're the same kind of math. So a spherical mirror is if you imagine having a big giant sphere in which we take one little slice of that sphere and we're left with a little piece of sphere like this, and it's going to be shiny on one side, either on the inside of that sphere or on the outside. If it's shiny on the inside, it kind of looks like a cave, right? Like the opening of a cave. And so these are concave mirrors. They're shaped like a cave, and this is where the inside of the mirror is reflective. If it's the other side of the mirror, so the outside of the sphere, that's reflective. Well, this is convex, shaped like a vex. No, there's not as fun of a mnemonic for this one, but it's not the concave one. So it's the outside of a sphere that's mirrored, and so this will be convex. If you think about that giant sphere that we used to make the spherical mirror that we lobbed off a piece, the radius of that giant sphere is going to be a big R, the radius of curvature. And so think about having these two spherical mirrors, these pieces of spheres, but one has a small radius and one has a large radius. You can see that a bigger radius is sort of more subtle in its curvature around the mirror. What do you think happens if we take that R to infinity? If we do that, we keep going and keep going. To draw a circle that's infinitely far away, it would have a perfectly flat uh, mirror to it. So if where R is infinity, that means we have a flat mirror. So now let's try to understand how these mirrors behave. And so to do this, we're going to have this concept of an optical axis. So we'll have a mirror, and we're going to draw a line perfectly straight through the mirror, straight down the middle, and this is what we'll call the optical axis. We're going to use this to think about how light it's going to hit the mirror and then reflect as it goes around. So let's first think of a light ray that's infinitely far away from the mirror. Okay, it's really, really far. Well, if it is, okay, then that light is actually going to go this way and hit the mirror, right? And if we think of this one piece of the mirror as being like a little tiny flat mirror, so we can think of this spherical mirror as being made up of a bunch of little flat mirrors. Well, the light ray that hits this part will follow the law of reflection, and it's going to bounce off. It's going to bounce off in this way where the incident angle equals the reflected angle, and it's going to go down in some sort of downwards direction. So it turns out the light that's infinitely far away is going to be parallel to the optical axis. In this picture, that means this incoming red line is going to be parallel to the blue line. If we keep getting more light rays, so more of these light rays that do the same thing, they're all parallel to the optical axis, what happens? If we do that for a spherical mirror, we get that they all converge. They all go through the same point on the optical axis. Okay, and so light that's coming from infinitely far away. So think of like the sun. The sun's pretty far. If you have a mirror and you point it toward the sun, a spherical mirror, point it towards the sun, all the light is going to hit one point, and we call that the focal point. For a spherical mirror, it turns out that F is equal to R over 2, where R is the radius of curvature. And so if you point this at the sun, you really don't want to be here because all of the light is hitting one spot. And think about what you can do with this. Something about ants. For convex mirrors, the analysis is the same, but the results are a little bit more funky, right? So we still have light that's parallel, but it's going to be reflected not really towards a certain direction, more like away from a certain direction. And we can do the same thing. We have a bunch of light rays. They will all reflect in a different direction. And so a bunch of light rays will go away from a certain point, which we'll still call the focal point. All that light will appear to have come from a source of light. So remember that light has no memory. So if you were able to collect that light ray and this one and put them all together, you would have no idea. You would have no way of discerning that this came from a reflection from an infinitely far away source. In your point of view, if you collected those light rays together, they look like they're coming from this point F. And so all these together would just look like something is at F, is what your brain would perceive. We still have F here. F is going to now be equal to negative R over 2. This negative is just, it's just a mathematical tool that's going to help us do some computations. But so this convex mirror is going to have a negative radius of curvature. And you can see that the focal point is behind the mirror instead of in front of it where the image is. So it's opposite the side where the image is. Sorry, not the image, the original object, which was the sun over here, or whatever infinitely far away source. The focal point is on the opposite side of that, and so that's where we're going to have a negative value. And light need not be coming from an infinitely far away source. It can be coming from a normal object, which is not infinitely far away. And only for the infinitely far away source will we have that light ends up at the focal point F. For something that is nearby, or just more in general, we'll have that an image will be created at a point, let's say F prime. This is what we call the focal plane. This is where an object's image has focused on the focal plane. And so think about multiple light rays coming from this object. They'll all bend in a different way, but if we trace them back, if we manage to trace back where this light came from, so once again, we're going to pretend that we're only allowed to collect this piece of light and that piece of light. I have no way of knowing that it was reflected. In my point of view, it looks like all this light came from an object over here, but it's not really an object, it's an image. All this was generated by this tiny little triangle square setup over here. And so you can see my perception is different. I wish I could show you demos, and I will when we come back. You'll have to experience the lab first, but where we can see tiny images of things around spherical mirrors. You can imagine looking at the back of a spoon. A spoon will be like a convex mirror. You should look at it and you should be able to see an image of yourself. But the mirror dimension U is a tiny, tiny person. We're going to use this concept of a ray diagram, which is where we keep track of all of these lines and the reflections. This is a ray diagram in order to identify where the image is. So using what we learned, we can think of 3 special light rays and the fact that these spherical mirrors kind of have these little planes of reflection. Use these 3 things together and we should be able to figure out where an image will be created. So the ones that I've come up with here is the green. Light that comes parallel to the optical axis ends up going through the focal point. So remember, the thing that's infinitely far away will go through the focal point, right? Well, if you think of this object, it's emitting infinite light rays in all directions. One of those light rays, the green one, will go through here And to the mirror, it looks like it's infinitely far away. So the mirror is going to go ahead and send it through the focal point right here where it's supposed to go. Now think of the red line. Light that goes through the focal point bounces off parallel. So this kind of works in reverse too. If there's light that came through the focal point, any light that comes through the focal point, it's going to leave parallel after it hits the mirror, parallel to the optical axis. And so once again, out of the infinite light rays coming from this triangle, one of them is going to be very perfect and it's going to go through the focal point and leave parallel. One more line to consider here. Light that goes through the center, if you think of this giant sphere here where this is R, it goes through the center, it's going to hit the mirror. And at the mirror, if you think about a circle, any light that goes towards the edge is going to be perfectly perpendicular to the edge of the circle, right? And so this, due to the law of reflection, it's going to come and bounce perfectly right back at you. And so light that goes through the center comes back. And what we find is those three light rays converge at one point that's going to decide where the image is. And so this will be the focal plane where a focused image of light is going to be created. And so this ray diagram is able to help us find this focal plane where the image is created, the image location. But yeah, just keep in mind that there are really infinite light rays escaping this triangle up here. They're going in all sorts of directions, but these three light rays are special in that this method uses these three light rays to identify where the image and where the focal plane is. So this is a very geometric thing, right? We didn't do any math. We just used logic and some drawing. This ray diagram method, it's a little bit limited in its accuracy because of that, but it's very useful as a sketch to understand a few things. Like, for example, look at this picture. This guy is upside down, isn't he? This image is upside down, and that's something that the ray diagram can help you discern. And so do take this slow, since this geometric optics portion of the class, it's not very big, but this is going to be a common thing that we're going to do. And so let me remind you the three light rays that we used here. A line that was parallel to the optical axis, it ends up at the focus. So this green is parallel to black, the optical axis, and so when it strikes the mirror, it ends up going through the focal point. The opposite to that is that light that goes through the focal point is going to end up leaving parallel to the optical axis. And so yeah, it's the sort of opposite to what we just saw. And the third one, light that goes through the center of this giant circle, through the radius of curvature, is going to go and then bounce right back. And we have our three light rays. If we put those together, we'll see that now they converge at one point, and we can draw where the image is going to be. If you have your spoon handy because you were eating cereal and you looked at the back of it for the convex image of yourself, turn it around and look at the concave face. And what you should see if you look at this thing, and if you're far enough away from it, you should see an upside down image of yourself created in that spoon. And that's this guy. Looks like a mini you in this mirror dimension, but upside down. This can change though. This is not always going to be the same. So check this out where we've got now an object, a real object between the focal point and the optical device here, the mirror. And so let's try this ray diagram again, but it's going to be a little bit more complicated. We still have this light ray that if light comes parallel to the optical axis, then it will leave and go through that focal point. So once again, that there's light that's going in all directions away from this object, but one of those light rays will be parallel to the optical axis, and so that piece of light will go through the focal point. The red cousin to that light ray is that light leaving the focal point will leave parallel to the optical axis after it bounces off the mirror. So think about this. There is a piece of light that looks like it's coming from the focal point. If there was a piece of light leaving the focal point, it would be parallel, right? Well, out of all the light rays leaving this object, out of all the light rays, one of them is going to appear to have come from where the focal point is. That piece of light is going to bounce off parallel to the optical axis. Similarly, any light that leaves the center of this giant sphere from which the spherical mirror is made, any light like that should bounce back from this right here. There's a 90-degree angle, should bounce back perfectly because theta r and theta I are both 0. And so if we once again consider that any light ray from this object is created, so in every direction, light is created in every direction from this object, one of these light rays is going to be going perpendicularly that way and bounce right back. But if we look at these, and let me do a little bit of erasing. If we look at all these light rays here, they don't really look like they're converging at any point, except maybe where the object was first created. And so what's going on here? I thought they were supposed to come together and form an image, right? Well, what we could do is carry this back. So again, this is the outcoming way that this light is coming from. And so imagine that I had a way of capturing this last piece of light. Where would it all come back and look like it's from? Light has no memory, so my brain, or my eyes, I should say, only perceive these to have been coming from one point. And so they look like all these light rays came from a place behind the mirror. We know that the light can't really be there, but that's what it looks like. And what you should see is that the image is upright, so it's not upside down, and it's going to be enlarged, bigger than the original object. Somehow our image is larger. And so this is useful, right? Like you can magnify an object. This is like a compact mirror. You're doing your makeup. You look at the mirror and you see, well, you can see every little pore and zit that's on your face because the image of yourself is bigger than you actually are. And what about a convex mirror? Well, let's try some of these light rays here. So light, there's one piece of light that's going to go parallel. There's another piece of light that's going to go towards the axis. I'll sort of do these for you with just a little bit of explanation afterwards. I think it makes more sense. And one piece of light that goes towards the center. And so you can see that like light that actually was trying to go towards a focal point, okay? Light that was trying to go toward a focal point. That one is going to come out and leave parallel to the optical axis. Okay, light that was going parallel will look like it came from the focal point. And light that was going towards the center of this circle will bounce directly backwards. And if you put all this together, you once again remember that light has no memory. And so in particular, this this parallel line here will just keep being followed as if it came from one location over that way. And you can see that altogether kind of, I know my drawing is very rough here, but it forms an image behind the mirror and smaller. Instead of bigger, this one's going to be smaller. So I know that one is fast, so we'll definitely practice that one in person, but you can see this is like the back of the spoon. You should see an image which is smaller than you. So that was a graphical geometric approach to solving the problem, but we can take a more mathematical approach and actually compute with numbers where is the image and where is the object. Using the rules of geometry and similar triangles, right? Look at these two grayed out triangles. We're following the law of reflection, right? So this is theta I, the incident, and this is theta r, the reflected. Well, this forms now two similar triangles, and that means the ratios are the same in similar triangles. So for example, this vertical one and this horizontal distance, HO, the height of the object, and DO, all the way to here, is the object distance. That ratio, HO over DO, is going to be equal to HI, the image height, over DI, the image distance. And so that's how similar triangles helps us form these little ratios. This particular ratio could help us find the size of an image and see how high it is based on how far the image is. You can take different pathways, like through the center of this giant sphere, and you end up with the same kind of similar triangle. I'm not going to quiz you on exactly what this derivation is, but mostly interested in the result. But yeah, so you have that these angles are the same, and therefore these two are similar triangles. Same kind of ratio laws apply. I won't go into the specifics. You can pause the video and try to understand exactly where this equation came from. But these ratios are going to be useful. Because if we combine the fact, well, so this just came from geometry over here, combine that with the fact that the focal length is half the radius of a giant circle that was used to create the mirror, you put those together and you come to this conclusion, which we call the mirror equation. And it's another one of these upside down ones, kind of like when we added resistors in parallel. 1 over f, 1 over the focal length, which is this value here, the distance from the focal point to the mirror, is equal to 1 over dO, the object distance, plus 1 over di, the image distance. So if you know two of these things, you can find the third. Usually you know what the focal length is because you buy your mirror and it says on it f equals something. And dO is something you can easily measure. That's the distance from the mirror to an object. And then di is often what you're looking for, not always. Often what you're looking for is the distance away from the mirror that the image is created. And so I think for now, this is really as far as the math equations we go are used. We'll practice that in the next slide here, but these are the equations just laid out for you. There's this mirror equation, 1 over f equals 1 over dO plus 1 over di. A little thing to note here, f can be negative. F can be negative for a convex mirror. If you got a convex mirror, then f is going to be negative. That will change where these images and objects are. So essentially, if you have a mirror and it reflects, you can create an image over here if it's real, or it's going to create one over here if it's fake, if it's a virtual image. It's going to create one on the wrong side of the mirror. And so this ratio here, HO over DO equals negative HI over DI, that's going to help us see how big is the virtual image compared to the original object. And finally, M is the magnification. It's just a ratio of how much bigger or smaller your image is compared to your original object. And so that can be handy. You want to know, are we magnifying it 2x, 2 times, 3 times, or just 0.5, so half as big. And so M is a unitless number because HI is in meters and HO is in meters. It's a unitless number which describes how much bigger or how much smaller the image has been magnified. So I'll let you practice with this example for which there is a solution posted as well along with this video. And we're going to have a concave mirror which is going to generate an image as we saw with our ray diagram earlier. It's going to generate an image which is upside down. And one thing I didn't mention, which you might need for tomorrow's lab or for Tuesday's lab, is the concept of real versus virtual. So a real image, to put it simply, for right now, a real image is going to end up being upside down, and a virtual image is going to end up being right side up. The difference is that this mirror, light that's coming from this guy is going to reflect and actually reach a real touchable location. If you put a screen, you put a piece of paper right here, well, guess what? You're going to see a little picture of an upside down arrow. And so that makes it real. Light is actually there. That doesn't mean that we've created a new object. We haven't just, broken the laws of physics and cloned our object. It's just that the light happens to focus at a real location. The virtual one is one which would be created over here. If there was an image created over here, I can't bring and put a piece of paper and expect to find an image because there's no light actually seeing this part. And so this will be a virtual image. On the other hand, just because it's virtual doesn't mean we can't perceive it. If you, with your eyeball looks at this mirror, you're going to perceive an object in the mirror dimension because according to your eyeball, the light rays that it's going to receive are all indicative of an object existing at this location. So yeah, so keep that in mind with real versus virtual images. Work on this problem. I would say see if you can try and fit things into the equations and get things out without worrying too much about what that means on the picture. And then go and look at the video on this problem to watch my solution and see if that matches yours, and then also try and understand then what do those numbers actually mean in terms of the picture. So as for a checklist for understanding, we're going to see if we understand how these spherical mirrors work mostly. That's the big bulk of what we learned today. But also just reading the ray diagram in general and trying to create your own. If you can do that, then you're in a pretty good spot. We just talked about the difference between real and virtual images. And finally, we can locate an object or an image based on the focal length. But all these points really require practice, so I don't expect you to be an expert just by watching this lecture. And so we'll take these concepts with us to lab, and hopefully that will help cement these ideas a little bit more as we get to more practice problems. All right, folks. See you in the next one.